Alright, so lecture 27 is on the Gauss Bonnet Theorem. We're going to look at at least a sketch of the proof. It's partial because we will be relying on some results from topology, which we will not prove. And also I would mention that the argument I give here is more or less what's in O'Neill. I think if you want to see something that's a little bit more detailed, there's a nice chapter in John Lee's Riemannian manifolds book, which has some arguments due to Hopf, and also contains a generalization of the theorem due to Hopf and Stern. And then also there's a book, it's either written or in the process of being written, by Leonid Schifrin, probably mispronouncing his name, which is, at the moment at least, available as freely as a PDF, and it has a pretty detailed proof of some of the things we're going through in here. So there's lots out there in addition to these well-known arguments I'm showing you here. Anyway, so if you have a regular curve from AB to M, suppose it's regular again, and an oriented geometric surface M, the total geodesic curvature of alpha is, by definition, the integral over alpha of the geodesic curvature with respect to arc length, right? So what that means is that we integrate from S of A to S of B, the geodesic curvature parameterized by S of t, of course, and times the ds dt dt. So I suppose we have not assumed an arc length parameterization here. I mean, ds dt, the speed, could be, doesn't have to be unity. Now, a good example of this is for the circle in the plane. So here, if I give it the arc length parameterization, basically divide by the radius, that gives me unit speed. There's the unit tangent. So here we're working in the Frenet, so working with two-dimensional vectors, I rotate the thing 90 degrees. Out pops this gadget right here. There's your Frenet normal, right? And then, so the geodesic curvature is just given by the inner product of t and t prime and n. Right? I mean, here the metric is the inner product, okay, so whatever. And out pop sine squared plus cosine squared as usual, and so we get 1 over r is the geodesic curvature. All right. So, while geodesic curvature and Frenet curvature are in general different, when they do match up, they match up. Of course, again, the geodesic curvature could be negative, whereas the Frenet curvature is essentially by construction positive. All right, so now that I got that out of our system, we integrate 1 over r from 0 to 2 pi r, and we get r's canceling, and we get 2 pi. A counterclockwise oriented circle in the Euclidean plane has total geodesic curvature of 2 pi. In fact, this is proved in Lee's book following Hopf for a so-called curved polygon in the plane. His chapter starts with a proof of that. It's pretty interesting stuff. Sorry, I'll stop advertising Lee's Riemannian manifolds book, but it is a nice book. Anyway, if you were to do clockwise, on the other hand, you pick up a minus, all right? Because if you go clockwise the other direction, the normal, I think you still, let's see if I can picture it. So this, excuse me, try to draw them both where you can see them. So that's the counterclockwise, right? So if I was to have a clockwise circle, oh, stupid whiteout, that's gonna smudge, oh well. The tangent would point, wait a minute. That's counterclockwise. Yeah, this is I forget which way is clockwise, which way is not clockwise. This would be clockwise. So basically that would amount to, we could think of replacing the arguments with minus the arguments. But basically that just makes it sine, cosine, all right? And so when you rotate, you end up with, I think, minus cosine plus sine. Minus cosine plus sine puts the normal out here for the clockwise. So that would be the difference, and that's why the geodesic curvature would be negative, because the circle is falling away from the tangent. So this would be the geodesic curvature less than 0. Of course, this is geodesic curvature positive, as we just calculated. But otherwise, the calculation would go through the same, and you'd get minus 2 pi. All right. So as I was mentioning, this is proof for an arbitrary curved polygon in Lee's book. Again, result due to Hopf. All right, corollary 4.6 we looked at last time was that the geodesic curvature is related to the angle between E1 and the velocity as follows. So it's just d phi ds plus the 1-2 connection form acting on the velocity of a unit speed curve, beta. So you look at this and you integrate, and out pops this wonderful, wonderful formula. So that the integral, the so-called total geodesic curvature around alpha, it's the change in the angle along the curve plus the integral of the 1-2 connection form along alpha, all right, for a regular curve segment, all right? And the proof of that is really just integration of that lemma we proved last time. Here's the proof. So integral of kappa GDS is by definition, we take the geodesic curvature, evaluate it the arc length function, multiply by the speed, S of A to S of B, but by U substitution, that's the same as this, right? But then the geodesic curvature is given by d phi ds plus omega 1 2 of alpha prime, we proved last time, and I mean alpha beta, I'm using, what was alpha? Alpha was a regular curve segment. I perhaps should have a beta prime here to denote the arc length reparameterization of the original regular curve. So, but if you can forgive me that notational discretion, we have this. But then, of course, the integral, well, fundamental theorem of calculus, integral of total rate of change is the total change, and of course, this is just the integral of the 1-2 connection form along the curve. And there you have it. Now this is, I mean, honestly, this lemma, I mean, I'm close to saying this lemma is the Gauss Bonnet Theorem. I mean, it's not quite accurate. This is important, though. I mean, this is the nuts and bolts of what most of what we do follows from this. Anyway, so continuing, suppose we have a 1-to-1 regular map from some, subset of the plane to M, and this means that there is a R tilde, which contains R, which is open, and X is regular on the extension to R tilde. So R could be closed, all right? So if we talk about regularity on a closed set, that means that you can extend to an open set on which it's regular, as we defined at the start. And then we now return to the discussion of 2 segments, which we had set forth in a previous chapter. So here's your 2 segment. And we do this funny thing, which is really smart. I mean, this is actually how I try to encourage Calculus 3 students to calculate, because honestly, I mean, yeah, Green's theorem and other things are set up for counterclockwise oriented curves, right? But there's just something like intrinsically error-inducing of using opposite orientations on Cartesian coordinate parametrized curves. So, well, I mean, to get the counterclockwise orientation, you maybe would want to use minus gamma and minus delta there, but don't. We make them, left to right and down to up for delta, beta, and gamma alpha respective, and so that gives us the so-called 2 segment, which is like a curved square, or curved rectangle rather. It's actually a rectangle over here in the parameter space, but then the patch X moves it up here, or parameterization moves it up to this curved rectangle. And the boundary of X is alpha plus beta minus gamma minus delta, because alpha and beta are going in the right way to go counterclockwise around the rectangle. But then, of course, delta and gamma need to be reversed. All right, this notation is not, it's not pointwise addition. Here we're talking about the addition, which is curve, like the curve following addition. So there's This is a slick notation for the concatenation of curves into a larger curve. I don't think I ever made that explicit, and yet I hope you understood it. There are other places and other times where making it explicit would be worthwhile. Specifically, if we were getting into the nuts and bolts of homotopy, I would want to get into that, but that's not here. So the natural induced orientation of the boundary makes the edge on your left while you walk on the top of M. Let me just give you the picture again here. So if you imagine walking around this is M, by the way, and you know, this is the top of M, right? Although my picture is just a picture, it's not, you know, fundamental. This surface could be inside, you know, 20 by 20 matrices. It could be a particular surface in 20 by 20 matrices. I mean, whatever. This is the abstract geometric surface, all right? But that said, you know, we also are assuming, well, since we're working with X, we can orient it. We can use the patch at least to orient this little 2-segment. All right. Now, or I should say we can use dm to orient it. Anyway, so let me stop. Move along here. So definition: X from R to M be a 2-segment M. The closed rectangle R from, you know, AB across CD has edge curves given by alpha, beta, gamma, delta, which in particular are, so for alpha, you let U vary, you freeze C. For beta, you let V vary, you freeze the U. And gamma, we take U as a variable, we freeze D, right? And delta, we freeze the U variable at A, and we let V vary. So if you go back to the picture I just had on the previous slide, these make sense if you look at it, right? So like alpha and gamma both have the same parameter froze, and beta and delta both have the same parameter froze. As you can see over here, they're pre-images. You know, alpha has V froze and then U varies, and same for gamma, but beta and delta have V as the variable, which is what we wrote down here. All right, so just a little bit back from chapter 4, just reminding you guys. So, with that said, alpha plus beta minus gamma minus delta is a simple closed curve on the boundary. Well, not quite accurate. This is the concatenation of these 4 curve segments. Simple closed curve, but it's not, you know, with stopping points, not quite, you know, not quite. We have vertices, all right? We have the joining points to the curves. So what's the total geodesic curvature at the boundary of X? I mean, this is true in terms of the point set, all right? That's definitely true. But the thing is, when you're calculating the total geodesic curvature of that boundary, you know, the corners matter, all right? If it was a single curve, we wouldn't have to worry about it, but the corners matter here because the angle can change at those corners, right? That angle between E1 and the tangent to the curve. So what we're going to have is the integral around the boundary is equal to that plus that plus that. And I don't think that's quite accurate. Plus what? Corner terms, right? Plus corner terms. All right. Now, here's a picture. But I mean, I'm just getting, as far as the boundary of X goes, it's this plus this plus this plus this, and then the minus pulls out because, you know, because this is an oriented. Well, because the geodesic curvature flips signs when you reverse the orientation of the, you know, the curve. curved segment more specifically. You say, oh wait! I remember from calculus 3 that the arc length integral it doesn't care about if you reverse the orientation. It doesn't change signs. Well, that is true, but we're not integrating this. This geodesic curvature is not an innocent bystander. When you reverse the orientation of the curve, it reverses its sign, as we just saw with our circle example at the start of this lecture. So that's why the minuses pull out, because the geodesic curvature flips. Now, excuse me. Plus the corner terms, right? And those corner terms is what we're going to talk about next. Here's a picture that's the start of it. All right, maybe this is all of it actually. So your curved rectangle could look something like this. And if I want to calculate the total geodesic curvature of like this purple, I've tried to draw like a purple curve. So you can think about it like, what's the total geodesic curvature of that with these rounded corners, and then as they kind of in the limit get to the corners, they have to pick. It has to match what you'd get from integrating the geodesic curvature along alpha, beta, minus gamma, and minus delta, respectively. And you'd also have to add in these other terms here from the turning of those. Let's see here. So again, if I just take, well, I guess I'm. Sorry, it's a question of notation mostly, but I shouldn't have crossed this out earlier. I'm sorry. Let me scratch that. The reason for that is he really does mean the boundary of x is just the union of these two segments. But the thing is, we're going to want to realize this as the boundary of a simply connected region in a bit. And so there, I need a nice boundary curve, and this is not that. I need this sort of curvy one in order to make a connection with the theorem later. All right, I'm sorry. It's no notational that's getting me here, but so he says C is the boundary of x with the corners cut. And so the integral around C is not equal to the integral around the boundary of x because, why? Because it neglects this neglects the turning, right, which you would have with the little purple curve. So let xr be pictured above. The vertices are p1, p2, p3, p4, and the exterior angle epsilon j of x at pj. So epsilon 2 at P2, 3 at E3, and so forth. They're derived from the edge curves in the order of occurrence, and likewise the internal angle is, I believe, supplementary to epsilon j, right? The sum of the internal and the external angles is pi. So like the internal angle will be like here for this one. The internal angle would be, if it extended that, would be like here, and so forth. The internal angle here would be like in here, and the internal angle here would be like there. Oh, I think I'm sorry, I was off the map. Goodness gracious. Sorry about that. Try that again. So the internal angle, if I extend this back, the internal angle would be like in here. If I was to extend this back, you could see the internal angle in there. If I extend this back, the internal angle's in here. Extend this back, the internal angle's like right in there. External plus internal, external plus internal, external plus internal, external plus internal all come out to pi, all right? So, well, here's some formulas that connect them, right? So, now, depending on the picture here, you know, we either have acute or obtuse angles, right? So, like epsilon 1, well, I have epsilon 2 equals to theta 2. Why do I say that? I'm sorry, guys. What's theta? All right, well, I say look over. I better follow my own advice. All right, so I say, I'm sorry, here it is. The coordinate angle theta is between 0 and pi, and it's the angle from xu to xv for these patches, all right? So like theta here, theta 3. So if xu, now which one is xu and which one's xv? It depends on which curve we're looking at, right? Remember, these are either u or v parameter curves. So it's just a matter of bookkeeping, but like this one is a v parameter curve and xv points that direction. This is a u parameter curve, right? And so xu points that way, but of course minus the curve points this way, and so the angle, the turning angle is the angle between where it was going to and where it's going, where it was going from and where it's going to. So this is the epsilon 3. Theta 3 is defined to be the angle between xu and xv. And the relation between the theta and the exterior angle is different at different vertices. So for example here, the sum of them is obviously pi, right? But if you look at similar pictures to prove the remaining assertions, well, let's do that. For example, over here at on the other edge of the rectangle, you have the, here's where xv would be pointing, xu is pointing that way, right? As my picture is drawn. Now epsilon 4 is over here, and theta 4 is over there. How are they related? Well, they're equal, right? Because that's actually a line, and that's actually a line. Just, it's kind of got a little bit bent in my picture, but it's supposed to be a line. So these are equal by elementary geometry, right? What are those, alternate interior angles or something? And so similarly, you can prove, as I was mentioning over here, that epsilon 1 is equal to pi minus theta 1, epsilon 3 is pi minus theta 3, but at those other two edges, because of basically what we just saw, epsilon 2, the exterior angle, is equal to the angle between xu and xv in those cases. So that said, sorry, there's a lot of things going together here, but once it comes together, you'll like what we find. So we have a regular 1-to-1 two-segment in a geometric surface M, dm the area form. All this notation put together, if we integrate k dm, Isaac, buddy, gotta play quiet, okay? Thanks. If we integrate k dm over this two-segment like that, well, it's equal to the integral over the boundary of the two-segment, right? Plus these exterior angles, and that altogether has to be equal to 2 pi. This is the Gauss Bonnet Theorem with exterior angles. All right. Now, here epsilon j is exterior angle at vertex pj as we defined. So this is Gauss Bonnet formula with exterior angles. In terms of the interior angles, you can also rewrite it as follows. The integral of, this is the total Gaussian curvature of the two-segment, right? This is the total geodesic curvature of the boundary, and that has to be equal to the sum of the exterior and interior angles minus 2 pi. All right. Now, we have sums of 4 angles because we're working with rectangles, right? There are similar theorems that you could prove for a triangle where you'd have the sum of 3 exterior angles and the sum of 3 interior angles, and I think you end up with pi and minus pi instead, but I should not. I haven't. I'm speculating. I haven't thought through the details there. I'm just. All right. Sorry. So here's the proof. Let me stick on what we're doing. So, based on the frame field associated to x, in particular, for this two-segment, we can set up the frame E1, which is xu normalized, and then E2 is j on E1. And that's chosen such that the dm is E1, dm on E1 and E2 is equal to 1. All right, so we're choosing the positively oriented frame. And then we recall the second structural equation. The second structural equation defined the Gaussian curvature for us. In particular, d omega 1, 2 is equal to minus k dm. But on the other hand, we also know that d omega 1, 2 plus k dm equal to 0 by algebra. So, great. Then what can we do? Well, we can integrate, and the integral is 0, 0. So we have the integral of d omega 1, 2 over x, and the integral of Gaussian curvature over the area form of the whole two-segment. But now we use Stokes' theorem, well, generalized Stokes' theorem, I suppose, which we have not proved, but you could prove. Anyway, so generalized Stokes theorem says the integral of the differential is the over the bulk is the integral of the integral of the exterior derivative of a form over the bulk is equal to the integral of the form over the boundary. So there we have it. But on the other hand, the relation between the integral of this form over the boundary and the interior angles or exterior angles in total geodesic curvature is somewhat complicated, right? And so by the lemma on the next page, this just works out to integral over the boundary of the geodesic curvature plus these turning angles, these exterior angles, minus 2 pi by the lemma on the next page, and that is the Gauss Bonnet theorem with exterior angles. All right, now, so here's the lemma. The integral over the boundary of the 1-2 connection form is equal to the integral of the the geodesic curvature over the boundary of x plus the turning angles here, minus 2 pi. Now, so to break up this integral, I've got this plus that, minus that, minus that. So what do we got here? The integral, and then for each one of these, we go back to that lemma or proposition theorem, I forget what we called it, in the last lecture, where we showed that the integral of the connection form along a curve was the difference in the phi angle plus the integral of the geodesic curvature along the curve, right? And so that's the thing, is this is non-trivial for these curve segments, right? And so let's see here. So I seem to be arguing that phi of b is equal to phi of a here. I'm not sure why. This is always 0 along alpha. Oh, that has to do with the definition, right? Phi is the angle between E1 and alpha, but when E1 is just alpha prime normalized, of course, the angle is the same because the angle is 0 essentially by definition of phi and by E1. All right. Okay, duh. Sorry. I get so much notation floating around I forget what's what. And then I talk myself into using theorems I don't need to use. Well, I hope you can sort through my my comments here to make sense of it. Anyway, so if we integrate along beta, again using the proposition from last lecture, we get phi of c minus phi of d. Now this time beta is based on the v parameterization, so there's no reason that this angle and that angle have to be the same. But these are those angles are the thetas, right? Because it's the angle between E1 and the tangent to beta, but that's the angle between xv and xu, the partial velocities of the patch, which is what we call theta, which by the way is the difference between pi and the third exterior angle. And for this one, and then the other one is on the flip side, the theta was just E2. So lo and behold, we get E2 plus E3 minus pi. Sorting through the details there. Here's some attempts at a picture. So E1, 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 right? And so this is the angle to start with, that's the angle to end with. And let's see, this picture could be improved slightly if I actually put in which vertex we're at. Let me do that. I think the numbering, hopefully I'm going to... So beta went from P2 down here up to P3 up here, right? Whereas alpha goes from P1 to alpha went from P1 to P2, right? And then continuing, the third one goes from, where did we go from? Come from P3 over to P4, but this time the angle is always pi, I believe. Let's see here. Yeah, minus gamma is opposite the E1 direction, right? So these are equal, so we just get the integral. We just get the integral of the geodesic curvature along gamma for the integral of the 1-2 connection form in that case. All right, one more to go. For the fourth curve segment, we have going from P4 back to P1 finally, completed the loop. I'll just draw P1 down here. I'm not going to try to draw P4 up there. It's too cluttered already. So there, of course, we have the integral along delta of the geodesic curvature, but we also have the difference in the phi angle, which the phi up here is like this. And so it's pi minus epsilon 1. Up here we have phi of d is epsilon 4, so we end up with pi minus epsilon 1 minus epsilon 4. So then when you put all four of these things together and add them, out pops the really cool thing, which is that the integral over the boundary of x of the 1-2 connection form is this plus that, minus that, minus that. But you get a minus pi here, you get another one here, so you get a total of minus 2 pi, and epsilon 1 plus epsilon 2 plus epsilon 3 plus epsilon 4. And there you have it. That's the lemma that we used to establish Gauss Bonnet theorem with exterior angles. So, you know, it's kind of overwhelming if you just look at it, but if you actually sort through the details, there's nothing here that is really beyond anyone's comprehension. It's just one step at a time. It's all not that hard to understand, really. Now, so that, I think, but goodness, the Gauss Bonnet theorem usually also involves that's part of the Gauss Bonnet theorem, really. I've been calling it the Gauss Bonnet theorem. I mean, that's the differential geometry side of the Gauss Bonnet theorem, right? Everything we did was just geometric about angles as it relates to a particular total Gaussian curvature, right? So this, just to be more specific as I'm saying this, so I've called this the Gauss Bonnet theorem, and so do other people, but the other thing that gets called the Gauss Bonnet theorem has a connection to something else called the Euler characteristic. Now we haven't talked about that yet. Here, this theorem just involves total curvature, geodesic curvature, these particular turning angles at the edges of the two segment, right? So again, this is totally a geometric discussion, right? Now what follows is topological. So, you know, one of the fundamental programs in topology is triangularization or rectangularization of surfaces. It turns out by making images of triangles or rectangles on an abstract surface, you can discover things about its topology. It's a way of detecting holes and all sorts of things. So this is a somewhat old story. I think Euler did some, those bridges of Kronosberg, but it's really coming to its own in the last maybe 150 years or so. So first, let's just talk about the idea of rectangularization. The idea of rectangularization is you take your surface and fill it with some curved rectangles, some two segments, as it were, and they have to completely fill the whole space and cover it. Obviously this isn't unique. I could take one of these and cut another one and add more rectangles, right? This door is a joke specific to the first time I taught the course, because one of my students got in this ridiculous argument with his roommate about a door, and I just wanted to bring it up again because it was a sore point. Anyway, stupid jokes aside, every compact surface has a rectangular decomposition. This is a special kind of paving, of course. Now, the proof is by scissors on page 369. The more serious answer is some of these triangularizations or rectangularizations are established in deeper books on topology. Lee mentions, I think, Massey's algebraic topology book, or what was it? What's the other reference? Alan Saradowski's Introduction to Topology and Homotopy. 1992. That's another place where you can find, I mean, there's probably lots of books that have these things proved, but we won't. The point is there is a rectangularization for a compact surface. Now, let's talk a little bit about the difference between, topology and differential geometry. So topology is concerned with what are the open sets, and also what are, what are the continuous maps. A map is said to be continuous in topology if it has the property that the inverse image of open sets is open. And so in topology, you can ask whether two spaces that both have topologies, which just means that there's a definition for what's open on those two spaces. And you can compare the sense of open sets on one versus open sets on another if you have a bijection between these two sets, right? And that bijection is continuous in the sense that it takes open sets here, inverse image open sets here, and if that bijection also has a inverse function which is likewise continuous, if you have both of those things, then that bijection is said to be a homeomorphism. Homeomorphisms are the maps in the theory of topology which preserve topological structure. So a topological invariant is one which is preserved by homeomorphisms. Just like us, we have talked about, well, we didn't talk too much about this, but diffeomorphisms are smooth mappings with smooth inverse. Smooth is much strict, is a more complicated thing perhaps than continuous, right? So diffeomorphism is bijection that is smooth with smooth inverse. And still different than that, we've also talked about isometries between spaces, where there you have a bijection, right? And the bijection preserves the metric from the one surface to the other, right? So it preserves this notions of distance and angle, because we've just talked about two-dimensional isometries, right? Of course, these comments have generalizations, but so you've got these different notions, isometry, diffeomorphism, homeomorphism, and what are the connections? Can you get from here to here? Can you get from there to there? What's the bridge between these worlds? Is there a bridge between these worlds? So it is true that diffeomorphism implies homeomorphism, because if it's smooth, it's continuous, right? So back to calculus 1 again, right? Differentiable implies continuous. However, continuous does not imply differentiable, and that's why we can't reverse this arrow. So, but that said, generally the converse is false. A homeomorphism does not imply that F is a diffeomorphism. That's why the following result is, in some sense, shocking. In dimension 2, M is homeomorphic to N, all right, as surfaces, if and only if M and N are diffeomorphic. That's very, very nice. Now, that's proved. I don't know if we'd prove that here. I think that's proved in topology books, but anyway, we will see evidence of that anyway. All right, like I said, we'll have to. I'm not sure that's proved in the text. I'm still not sure. I kind of think not. So theorem 6.6. Now this is a theorem we're borrowing from topology. All right. If D is a rectangular decomposition of M, a compact surface, let nu, E, and F be the number of vertices. I'm going to say V. Let V, E, and F be the number of vertices, edges, and faces in D. The integer V minus E plus F is the same for all such decompositions. Moreover, this integer is called the Euler characteristic. All right. So the Euler characteristic of M is V minus E plus F. Maybe after this I'll add a little video showing you how to do this for a triangularization of a sphere. I don't have it in these notes. I mean, I have some pictures here, but maybe I'll do some arts and crafts here after this lecture to add something here. Anyway, the proof is given in topology, but this equally well applies to polygonal decompositions. I said see the handout from Lee's text. Well, how about just go buy a copy of Lee's text and read it. But so the sphere, for example, has Euler characteristic 2. One, basically you can just take you can imagine in your mind's eye taking this tetrahedron, right, and just kind of blowing it up into these curved tetrahedron, like curved triangles that fill out the sphere, the edge of the sphere, and so that gives you a triangularization of the sphere. It has 4 vertices. It has 6 edges. 1, 2, 3, 4, 5. The one in the back, 6. And it has 4 faces. So 4 minus 6 plus 4 is 2. That's one, polyhedral approximate of the sphere, triangularization. Rectangularization. Rectangularization, similarly, you can imagine inscribing this rectangle or cube inside a sphere, and then just imagine those edges kind of blowing up to fill the edge of the sphere. Now, that process obviously does not preserve lengths and angles, right? This is not a geometric process I'm describing. It's a topological process, because we're talking about a distortion of geometry in particular, in the sense of distances and angles being distorted. But anyway, you can imagine in your mind's eye blowing it up and getting a sphere, so this gives you rectangularization. And then if you do the counting here, we have 8 vertices, we got 12 edges, we got 6 faces. It still works out that 2. Now, of course, that is not a proof of the invariance of the Euler characteristic across different possible rectangularizations of the sphere, but it does make us feel good about it. All right. So the torus has Euler characteristic of 0. I say I don't see it yet. I think I have, maybe that's one I should do in the separate video. Then that would add some goodness to these notes. All right. So another thing we can do is we can add a handle to a compact surface, and that will reduce the Euler characteristic by 2. So adding a handle is like pasting a donut on something else. So here's your initial surface, and then glue on this donut like that. And so if you think about it, if you believe that the torus has Euler characteristic 0, the net sum of v minus e plus f is 0 for this thing, right? And in the process of gluing it, what happens is you delete a face from both, right? And let's see here. You delete a face from both. What about edges? I guess you still have the same number of edges and vertices as you did before. I'm not sure I believe that. Seems like you're adding, I think you're adding, goodness gracious, I would say on M you're adding 4 vertices and 4 edges, but v minus e is 4 minus 4 is 0, so yeah, that makes sense. So basically you're just losing the 2 faces, and the edges and vertices even out, because you have plus vertices and minus edges. So the other characteristic of the surface with the handle glued on it is equal to the original Euler characteristic minus 2, which is kind of cool. And that gives us this theorem. If M is a compact connected orientable surface, there's a unique integer h greater than or equal to 0, such that the surface is diffeomorphic to a sphere with h handles, with h donuts glued onto it. All right, a sphere with h handles attached. It's a theorem. Now, a corollary to that theorem is that compact orientable surfaces M and N have the same Euler characteristic if and only if they're diffeomorphic. So if the Euler characteristic of M is equal to the Euler characteristic of N, that means that M and N have the same number of handles. Then by theorem 6.8, M and M are diffeomorphic. All right. So getting back to Gauss Bonnet, the full version of it. The total Gaussian curvature of M of a compact orientable geometric surface M is 2 pi, all right, times its Euler characteristic. Whoa. You're like, what happened to the geodesic curvature and And the exterior angles, why, where, it's the Euler characteristic, right? This is a really beautiful result because it links, right, the totally geometric quantity of the total Gaussian curvature of the surface to this intrinsically topological invariant of the Euler characteristic. So here we have worlds colliding, as it were. All right. The orientation of M by the area form dm, and we'll let D be the rectangular decomposition of M whose rectangles are consistently oriented with dm. That means that D is an oriented paving as discussed and defined in section 6.7, page 302. By definition, the total curvature of M is, we have to integrate over the paving, right? Total curvature of each, each tile in the paving, if you like. And where F is the number of faces, right? So the number of faces, which is the number of rectangles here. Now, you apply the Gauss Bonnet Theorem, but Gauss Bonnet formula. Probably should have been calling it Gauss Bonnet formula. That's why I'm confused. Words. So anyway, the Gauss Bonnet, I've called it theorem, but it's really the formula. The Gauss Bonnet formula to each face, and then we have what? We have the integral of kdm over the face is equal to this, since I've written it in terms of the interior angles, right? But every face is adjacent to another face, and so the boundaries are overlapping. In particular, we have that the integral over alpha I plus the integral of alpha j, I think that's supposed to be, I've lost my kappa. The geodesic curvatures, they cancel. So because of the way that I hopefully have a picture, it's the same kind of argument that we use in Calculus 3 to prove, like the various theorems for surface integrals where we break it up into pieces, and then on the separate pieces you have, counterclockwise orientations on each piece. So, stink. Do I have room to draw something here? So like there's two cells, two faces, right? And so they have to be consistently oriented like that, right? So on the one side, you're going this way, right? But on the other side, you're coming, when you hit that leg, that boundary curve goes that way. So when they're in interior, these interior legs, these interior edges, they meet up with opposite orientations, so these integrals cancel out along those interior canceling edges. That's why you end up with like integrals over the boundary of surfaces, because these interior terms tend to cancel. Anyway, okay, getting back to the proof. So all of the integrals over the boundary of these geodesic curvatures cancel as we integrate over all faces. And moreover, there is no external curve, right? We're talking about a compact orientable geometric surface. Sometimes this is called a closed surface. There's no edge, all right? There's just interior face. There's only interior edges is my point, all right? So the fact that these cancel means that these terms completely drop out. Moreover, the sum of the interior angles is 2 pi at each of the vertices, which makes sense if you think about it. Thus, by applying the Gauss Bonnet formula, we have the integral of the total Gaussian curvature is the sum over the number of faces of minus 2 pi plus the sum of the interior angles. But of course, the sum of a constant f times is just that constant times f, so that gives us a minus 2 pi f. And then we get sum I equals 1 to f of the interior angles of the ith face. Alright, but the interior angles of the ith face is just given to us. I say that that's 2 pi v. Why is that? Well, the claim sorry. Why is that 2 pi v? Let me just stop and think for a minute here. Why should the sum of the interior angles of the ith face work out to 2 pi times v? Now f is the number of faces, right? V is the, what is v again? V is the number of vertices. Curses. Why is that v? Maybe if we look at the examples on the next page, it'll become clear. Let's see here. So here, for example, is a rectangularization of a rectangle. So the claim is that 4f is equal to 2e. That doesn't help me see why that sum of the interior angles for the ith face was 2 pi v. What's the relation between number of faces and number of vertices? Each face gives you how many vertices? Well, it gives you 4 vertices, right? But some of those are shared, right? So I mean, you can't just say that there's man, why is that 2 pi v? Goodness gracious. It must be something simple I'm just missing. Oh man. Alright, well I'm going to leave that as, at the moment, an exercise for the reader. I must go on here. This is something you can check for different rectangularizations. 4 times f is equal to 2 times e. So let's see here. 4 times f is 2 times the number of faces. 4 times the number of faces is equal to 2 times the number of edges. And you can check it out. It works for this example, but that's generally true. So proof continued. More often than not, when I get stuck on something like this, the answer to what I'm stuck on is in the next little bit, and I just forgot. But anyway, here we go. Each face has 4 edges, but each edge belongs to 2 faces. Thus, 4f counts e twice. That is, 4f equals to 2e. All right, that's from O'Neill's page 374. All right. So the Euler characteristic was defined to be v minus e plus f, but that works out to v minus f because this gives us that minus f is equal to f minus e by algebra. And so f minus e is just minus f. So, which does actually kind of make you wonder, like, oh, I'm sorry, this is for rectangular decompositions. You know, if you look at other books which have proof in terms of triangularizations, these arguments, these little details here get distorted into other little combinatorial, factoids like here 4f equals 2e. All right. Anyway, returning to the total curvature is equal to 2 pi v minus f, but that is the Euler characteristic. So we get the total Gaussian curvature is 2 pi times the Euler characteristic. And I'm sorry, I still have not explained why it is that the sum of the interior angles of the ith face works out to v times 2 pi. I mean, what is the sum of interior angles of a particular rectangle? Well, that's pi over 2 plus pi over 2 plus pi over 2 plus pi over 2, I believe. So it seems like you got 2 pi interior angles for each face. But 2 pi v. Man, I am sorry. I don't. I don't see that. That's just me, though. I'm sure there's some obvious reason. Oh, and that brings us to applications of Gauss Bonnet, which is the next lecture. So I'm going to stop here. I hope I made some sense. I'm sorry for the mangling of terminology. I think at the end of the lecture you can see all of my transgressions. I called the Gauss Bonnet theorem the Gauss Bonnet formula. I mean vice versa. I should have said it was the Gauss Bonnet formula back at the start of the lecture. And what was my other abuse of terminology in here? The other thing was it really was the boundary of x. It wasn't not the boundary of x. It's just that to calculate the total geodesic curvature, to calculate the change in the connection form around the boundary, you have to take into account the change of the angle. So anyway, I will stop it here.